So in this additional lecture for the Statistics 2 lecture series, we're going to be looking at a slightly more advanced topic of how we actually derive estimates of this best fit line with ordinary least squares. I'm not going to go into the matter in a lot of detail, but at least provide a bit of an introduction and overview for those of you who might be interested in taking more advanced courses, or at least having a better idea of exactly how it is that we're able to estimate a line through a set of dots where you can't just draw one like a standard 2 points makes a line in geometry. So again, the goal here is to estimate the relationship between two variables, x and y. And what we're in essence trying to estimate are these population parameters where we have our beta hat 0 is going to be the estimate of the intercept of the line, and our beta hat 1 is going to be the slope of this line. We're also interested in estimating the error variance. So in essence, the sort of the degree to which the individual y's are scattered around this line. So that's going to be sigma squared. So one thing we might want to ask is basically what type of properties would a good line have? So, right, you could think that it might be that a good line would be one that minimized sort of the distance of each individual point from that line. Of course, that becomes sort of problematic if you think about the idea that some are going to be above or some are going to be below. You might also want a line that, say, has is an unbiased estimator of the actual population parameters. So we have to sort of think about, we don't want one that's, say, on average too high or too low, or that it gets something wrong. So again, very much like our estimates, we thought about them before, or sort of our measures, we're thinking about sort of we want them to be low variance, unbiased, accurate, right? Very much the same thing that we're interested in now. So in this case, what we're going to have is we're going to have our, basically, if we imagine there's some observed level y, it's going to equal some y hat plus this error term. We want this expectation of these error terms to be 0. So that means on average, we've got something that is unbiased, which seems fairly obvious. And we also want to minimize the sum of the squared residuals. Again, we aren't using absolute value for reasons that a little bit too complex to go into, but you can imagine that in essence it might overweight some observations versus others, and sometimes we want to actually have it to be somewhat sensitive to outliers. But again, this is very much the same as thinking about things being sort of accurate and unbiased when we think about measurement, and again, low variance. So these are the goals then, are basically to have something that is on average, the errors are going to be 0, and also these errors are going to be minimized. So recall that we looked at this in the earlier lecture, that the error terms are basically the distances between a single point that's actually observed and this estimated line. So again, when we're thinking about this, what we want to have then is the sum of these overall is going to be 0, and basically if we square them all and then take the sum and square root of that, then we want that to be as small as possible. What that means then is we're basically minimizing the noise, or the unexplained variance, which is defined as the residual sum of squares. So the residual sum of squares here, just as the sort of fancy math part, basically this is the sum of the EI squared. And you can see that's basically the yi's minus the y hat squared. So you can, in fact, we're minimizing this number, this residual sum of squares number. Why we're squaring the residuals, I think I mentioned this some in class, that there is sort of a practical interpretation that has to do with sort of the relative weighting of different observations. But there is, in fact, a geometric interpretation that has to do with sort of the Pythagorean theorem, and that what we're sort of dealing with here then is we're basically finding the shortest line, assuming that our sort of true x beta or x beta hat, that the y that we're observing we're basically finding the shortest line. And it just so happens, if you look at it like in this geometric sense, right, that using the Pythagorean theorem, it's the square root of the two things squared. I can't give a lot of intuition behind that, but that's basically the idea behind using square residuals, is it also that it corresponds to this geometric notion of shortest distance. So what are the key definitions then when we're thinking about these OLS estimates? This is just to help you sort of interpret some of the math here. We've got the mean of x, the mean of y. We've got the sum of the cross products, or the covariance of x and y, and also the sum of squares for the x's. So this is just the variance of x, and also the sum of squares of the variance of y. And again, these are times n by 1 because it's actually, that sort of deals with all of our n by 1s. It makes it a little bit easier to express things whenever we want to look at what, in essence, what our estimates sort of reduce down to. So, and we've already talked about the residual sum of squares. So to derive the estimators, and again, I'm not going to go into a lot of detail about this, but in essence, what we're interested about is we want to find a number such that the expected value of our residual sum of squares divided by beta 0 should in fact be, in essence, we're trying to find that such that the expectation of the error term, right, the sum of all the error terms is actually 0. And what we find from that is that it's basically the mean of y minus our estimate for the beta 1 times by the mean of x. And so that's what going to be our intercept is going to end up being. And this gives you some sense of how we actually then go and derive this. So again, we're sort of taking derivatives here. And this time what we're working through is the idea that when we're solving for beta 1, again, we're sort of trying to minimize the residual sum of squares given beta 1. So if you look at the last one, we're minimizing the residual sum of squares given beta 0. Here we're getting minimizing, so we take the derivative, we set it equal to 0, and we go through and we work out. And what we find is that it's basically the back to these definitions, sxy over sxx. In matrix notation, this is going to look like x prime x inverse x prime y. You can also think about it as like covariance of x and y over the variance of x. And now you can see why, looking back at here, the sum of squares, what we've done is we've sort of gotten rid of these n minus 1s in essence. But really, it's just a version of sort of the variation of x and y divided by the variation of x. Again, matrix notation, slightly different, but it works out to be the same idea. So these OLS estimates of beta hat, then again, looking at back at our earlier notation, what you can see is that, again, covariance xy, or sxy divided by sxx, and beta 0 is just the mean of y minus this beta 1 that we can calculate times the mean of x. So these are our best estimates using ordinary least squares. This is how we actually come up with estimates for our different beta hats. And by doing this, we end up with basically an estimate of our sigma EI, so our variance of EI, that should in theory be unbiased and as small as possible, right? And you can see, as you would expect, that it's like the change in x over change in y. It's just covariance of x over covariance of xy over variance in x, because it's not quite change in x over change in y, because we've got these multiple points, right, in our line.